There were some more population genetics wrinkles I was going to throw at you folks, but there's really not time. We could spend the entire class on population genetics, and in some departments they teach entire courses in it. But I need to move on just a little bit. I want to talk a bit about how evolution deals with traits that are continuous. By which I mean traits that are not grouped into a small number of phenotype classes. As in, Gregor Mendel's pea plants could be white, or they could be purple in their flowers, or an ear of corn could have red kernels or purple kernels, or what have you. All of these traits fit into a small number of possibilities. Continuous traits, on the other hand, vary over a continuous range. I think I've said this before, but humanity is not either basketball forwards or horse racing jockeys. Some of us are very tall, some of us are very short, and most people fall somewhere in between. There is, in fact, an inheritable component of height. Tall people tend to have tall kids, and short people tend to have short kids. But there is no single gene for being tall versus being short, as there is in pea plants. This was the subject of a lot of debate in the early 20th century between the folks who were Mendel's fanboys and a group called the biometricians. And it's largely been resolved because we now realize that you can have a trait that's inherited genetically, and yet many, many genes might be influencing it. There's no single gene for height. There's probably a couple of hundred, all of which can influence your height in some way. There's at least 9 major genes that have an impact on skin color. Which is another trait that varies on a continuum. We're not all either black or white. And now I've just got the Michael Jackson song in my head, but we're not really black or white, ebony or ivory. We range from deathly pale to deep ebony, and most of us are somewhere in between. So that's another continuous trait for which there are many genes that influence it, but no single gene that determines our skin color the way that a single gene determines a pea flower color. And I'll start with a rather horrifying example, and then I'm going to see if we can knock it down today and especially tomorrow. If I can remember how to push the button. I was in grad school in 1994, and a book came out by a Harvard psychologist and political scientist at this group called the American Enterprise Institute. The book was called The Bell Curve: Intelligence and Class Structure in American Life. And it stirred up an enormous amount of controversy at the time. The book is very cleanly written, calmly, academically. There are charts, there are graphs, there are data, and it tries to demonstrate the following proposition. Ethnic differences in cognitive ability are neither surprising nor in doubt. Large human populations differ in many ways, both cultural and biological. It is not surprising that they might differ at least slightly in their cognitive characteristics. One message of this chapter is that such differences are real and have consequences. Okay, I'm not sure if you noticed quite the size of the depth charge that these guys just dropped, but the claim that they are making is that there are, on average, differences in intelligence between what we call human races. Boom. Okay, for the record, since we have representatives of several human races in here, for the record, I happen to think this is crap. But I'm going to go through it and try to demonstrate in a calm manner why I think it's crap. both to help you answer arguments like this if they should show up, and also because it's a pretty good introduction in general to how we handle inheritance and selection and evolution on continuous traits. Intelligence certainly is one. There is at best rather peppery debate as to just how much of what we think of as intelligence is captured by IQ scores. And that's an argument I'm not sure I'm qualified to get into. You can go bother the folks in psychology about that. But whatever IQ captures, it is a continuous trait. You know, we are not all either Einstein or some dude dumb as a stall. Anybody know that expression? Staub's an old Ozark word for a fence post. And actually had a professor here who was family been in the Ozarks from way back, who was known to refer to certain people as dumb as a staub. So there, dumb as a fence post. We're not all either Staubs or Einstein. Some people are brilliant. Some people can't tie their shoes, and most of us are somewhere in between. So whatever IQ captures, it is a continuous trait. The authors of the bell curve argue that it is genetic, at least in part, that your IQ can be determined in part by your genes, and that since genes for physical traits vary among racial groups, like if I go to Sweden, I'm probably going to see a lot more pale people than if I go to Kenya. If those can vary, they argue, not me, they, the genes responsible for human intelligence can vary as well. And they happen to vary in a particular way that's all too familiar. This is a graph from the book. They took data from, this is called the National Longitudinal Survey of Youth. Basically a long-term experiment where they gather psychological data on human populations for many years. And this is what you got when you measured IQ. The white distribution is shown here in light. And the smartest white people that they found were about 145 IQ. The average is very close to 100. Below, I think 75 is supposed to be pretty much the minimum for being able to live completely independently. And it slows down here to about 55. All right, that distribution, by the way, is called a bell curve. You've probably heard that term before. And it's pretty typical for a value that's determined by lots and lots of factors and not any single one. And the bell curve for the white population in the NLSY peaks at about 100. The bell curve for the black population in the NLSY peaks at about 85. There are still some smart black people. That curve tops out at about 145. But on average, black people are about 1 standard deviation less intelligent than white people. Yeah. If this makes you pissed off, that's fine. I am too. Because I think I'll be able to demonstrate, once I've talked about how traits like this work, exactly where Murray and Herrnstein's analysis went completely off the rails. This is a book that a lot of people have, it was a bestseller. It's inspired people. There are people today that are using arguments like this in support of government policy changes. This is not some airy-fairy dispute about inheritance in pigeons or something like that that nobody really cares about. And I think I can demonstrate why they've made some pretty bad mistakes in drawing the conclusions that they have. This modest little proposal stirred up quite a bit of controversy. This is a book that came out that was a rebuttal to the bell curve. This came out a couple of years later. both the bell curve and this, the bell curve wars, are in the UCA library if you want to explore this sort of thing for yourself. But let's delve a little deeper into this. We won't finish today. We will have to go on to Friday, but let's see if we can't evaluate this. And in order to do it, I've got to step back a bit away from issues like this and just talk a bit about how evolutionary biology works with inheritance and evolution of continuous traits. Once we've got that back behind us, we'll be able to take a harsher look at Murray and Herrnstein. Okay, again, quantitative traits are traits that vary on a continuum. So height, weight, length, size of any particular body part, whether it's length of the arm or surface area of the leaf, various measures of intelligence or behavior or things like that. Those are all continuous variables. They're quantitative traits. And quantitative traits are determined by the actions of multiple genes. There's no, I said this before, but there's no single gene that makes you either tall or short. There are a lot of genes. There's no single gene that makes you athletic or not. Last I looked, they had identified something like 250 genes that have some correlation with athletic ability. I would be surprised if that's all there is. But, you know, athletic ability is also a quantitative trait. You know, some people can run, you know, some people are Usain Bolt and some people are George Washington on Mount Rushmore, right, who cannot run very fast at all. And most of us are somewhere in between. And there is, in part, a genetic basis for that, but there's no single gene for it. Quantitative traits also have a way of getting affected by the environment you're in. You can be born with Usain Bolt's genes for speed, and if you end up spending your life sitting in front of the TV, eating potato chips and watching, I don't know, what is everybody watching these days? Game of Vikings, Smallville Farms, or Thrones, or whatever the hell it is. You know, like a roommate I had many years ago, if you spend all of your time lying around the house and watching endless repeats of Family Guy, American Dad, and Whose Line Is It Anyway, you will not develop into Usain Bolt. Your abilities are conditioned in part by the environment you're in, and in athletics, specifically by the training that you're in. You know, I'm assuming you've got pretty good genes for jumping high, but I also assume that you've been practicing this quite a lot if you're a good enough volleyball player to get on a university team. And training and genes can interact in very complicated ways. And I don't know, again, I'm probably not the best person to talk about that in detail, but we can, in fact, do natural or artificial selection on quantitative traits. If you have a flock of pigeons, you know, the pigeon's weight might be a quantitative trait, and without even worrying about the genes that are involved, you can simply just save your biggest pigeons, breed from them, grill the rest on the hibachi or whatever you do with excess pigeons, and repeat that over many generations, and you'll get a breed of pigeons that's larger. People do that all the time. So you can do either artificial selection or observe natural selection on quantitative traits like this. And there's three basic ways it can happen: directional, stabilizing, and disruptive. And yes, those are things you do need to know. I think a couple of these were on the practice exam. They weren't on today's exam, but you might see them on exam 2. So word to the wise is sufficient. Directional selection, you're moving the mean phenotype. In stabilizing selection, you're favoring the mean and acting against the extremes. And in disruptive selection, you're favoring the extremes and you're selecting against the mean. And I'm going to cut over to the whiteboard right now. Because I want to give you guys a little diagram of how this works. Or bigger. All right. Okay, let's say here that we have, we'll draw X and Y axes. Those are terrible. Okay, there, I'll draw a graph. There's an XY axis. That'll be another one. That'll be another one. Okay, let's say we've got some trait. Doesn't matter what it is. Let's say it's, what the heck? Let's say it's the weight of pigeons. So we have a flock of pigeons. And we have, some blue. And we have a few pigeons that are really, really tiny. And most of our pigeons are kind of in between. Okay, we have a few of our pigeons that are really tiny. Most of our pigeons are kind of in between. And then we've got a few pigeons that are really, really big. We've got a few like Chungus pigeons. Did I use that right? My kid keeps using the word Chungus, but he doesn't seem to explain exactly what it is. Okay, we got a few, all right. My wife calls one of our cats this a lot. We got a couple of pigeons that are chunks. Chunks. Yeah, we got chunk pigeons over here. There's the chunk pigeons. And over here, we've got the teeny pigeons. All right. And most of our pigeons are somewhere in the middle. And if this is a true bell curve, the mean, the average pigeon size, is going to be the same as the median, which is the value right in the middle of the distribution. And they'll both be the same as the mode, which is the most common value. All right. So let's say we want to do directional selection. What we can do is we save only the biggest pigeons. We save only the chunks, the heck and chonker pigeons, and we encourage them to breed. And all of the pigeons that are not chunky and all of the pigeons that are not thick with two C's, we get rid of. We barbecue them or whatever we do. And after a few generations of this, our graph might look more like that. That's directional selection. Our original mean was right here in the center. And after saving all of the big pigeons to breed from and getting rid of the rest, the mean has moved. It's now over here. We could measure the amount by which it's moved. And that's directional selection. We're shifting the mean. The mean is going in a particular direction. And I mean, this is done all the time. If you're trying to develop bigger chickens or chickens that lay more eggs or tomatoes that have bigger fruit or something like that, directional selection is what would come into play. So this is directional selection right there. bit. Now, what would stabilizing selection be? All right. Okay, for stabilizing, imagine that we've got the same thing. We've got a population of pigeons. We've got a population of pigeons. And again, some of them are teeny, some of them are heckin' chonkers, and most of the pigeons are kind of in between. Stabilizing selection, you select against the extremes and you favor the mean. So let us say that we take all of the small pigeons and we put them on the barbecue, but we also take all of the really big pigeons and we get rid of them as well. So we're getting rid of both the small and the large. If we do that over several generations, we'll end up with something that looks more like this. Okay, I'm going to do the blue line as the before and the red line as the after. The average hasn't changed, right? The mean value for, after is right there. And the mean value for before selection is right there. The average hasn't shifted. What shifted is the variance. The bell curve has not moved, it's become more narrow. That would be a good example of stabilizing selection. And then finally, your final example is kind of the, conceptually, it's kind of the opposite of stabilizing selection, and it is called disruptive selection. And in disruptive selection, let's say that once again we have a nice population of pigeons with some really big and some really small and the rest kind of on the in-between. Now let's say we start saving only the really big pigeons and the really small pigeons, and the medium ones all end up on the barbecue. So we're selecting against the mean and we're favoring the extremes. What we would end up getting would be a curve. It might look like this. It's going to be a much wider curve. It might even have a pair of peaks instead of just a single peak. Now, again, in disruptive selection, the mean doesn't change. The mean after selection is still going to be right there. And before selection, it's still going to be right there. So, the center point of that curve has not gone anywhere. But what we now have is a much wider curve, and we're favoring really small pigeons and really big pigeons. But like the church in Laodicea in the book of Revelations, the ones that are neither one thing or another, the ones that are in between, are the ones that are getting destroyed. If you wanted to make this a tiny bit more real world, let's say we have a flock of pigeons and somebody introduces a small predator, maybe some feral cats get in there. If we had a situation where the small pigeons were getting overlooked, or maybe were quicker at flying away, and the large pigeons were big enough to beat up the cats, but the medium-sized pigeons were neither small enough to hide or large enough to fight, then the cats might eat the medium-sized pigeons primarily, and we'd be favoring the extremes, the small and the large, against the medium. That's disruptive selection. Okay, are we happy there? All right. Let's see if we've got some examples of, we've got some nice examples of both. So this is some actual data from the Galapagos. There was a couple named Peter and Rosemary Grant who have been visiting the Galapagos every year for 50 years now. They're faculty at Princeton. They've recently retired, but they're still going. And they've been watching year-to-year changes in the populations of finches. They are the world's top experts on Darwin's finches. Remember all of those finch species that Darwin found on the Galapagos and tried to figure out how they got there. Well, they go out, they trap a bunch of finches and measure things like beak size and other things like bird song and such. There's lots of data, different types of data that they gather. And they documented this. The Galapagos, I mentioned they're on the equator, but they're not your perfect little tropical islands with lots of cool breezes and fruity rum drinks with paper umbrellas in them. It's not like sitting on the beach in, I don't know, is Ipanema a good place?
It's a great place.
Okay. The Galapagos is not like that. The Galapagos is much harsher, and they're subject to the effects of the El Nino oscillation, which means that every few years they get slammed by drought. And this is what happened in 1975 through 1978. The grants had been measuring beak size, and there's a way that I'm not going to get into. It's called principal components analysis if you want to look it up. But it's a way by which you can take a whole bunch of measurements on a whole bunch of objects and boil them down into single scores. So you could measure beak width, beak height, beak gape, height of the upper beak, height of the lower beak, width of the upper, width of the lower. You could measure all of those. And then there's a fairly simple, well, it's really tough to calculate by yourself, but computers do it really easily. There's a way to crunch up all of those numbers into a single score that expresses what's making beaks different from each other. And that's what that overall size means over there on the left. That's actually a score called the first principal component, and it's what it says it is. It's a measure of overall size, taking several dimensions into account. Anyway, there was a pretty rotten drought that hit in between June through November of 1977. And right when that drought hit, you'll notice that the beaks of all of the Galapagos finches, the size shot up. This is not because the finches were all growing bigger beaks. What's happening is that finches that had smaller beaks no longer had food. Finches that had smaller beaks are adapted to eat smaller seeds. And drought caused the death or the failure to flower of plant species that had smaller seeds. So what happened was that the finches with smaller beaks were likelier to starve. The finches with bigger beaks, which would crack bigger and tougher seeds, those were likeliest to survive and have offspring. And once the drought was over, the entire population of Geospita fortis, the medium ground finch, had bigger beaks than they did before. And that's as nice an example as you can find of directional selection. Right? Beaks had always varied in size. There were some that were a little smaller and some that were a little bigger and most in between. And the average size of all beaks got larger after the drought. That's directional selection. So we're clear, this is not Lamarck. This is not because the finches all started working out to make their beaks bigger. It's not like they're all doing beak Zumba or beak squats or beak lat pull downs or anything like that. It's because birds with small beaks were likelier to die and birds with large beaks were likelier to live. So that's directional selection. Great example of stabilizing selection. This is some older data on human birth weight. And I believe it was gathered in the 50s before C-sections became nearly as common as they are now. They tend to be a lot more common these days. And before the dates of C-section, first of all, small babies have always been at increased risk because that usually means that you're premature. And for this data, for babies that were born at a weight of 2 pounds, that's a bit less than 1 kilogram, the percent mortality was nearly 70%. Where it says percent mortality over here on the right, that goes with these dots. Right? So you get the highest mortality with babies that are about 2 pounds, or 1 kilometer if you like. You also get increased mortality up to about 15% in babies that are 10 to 11 pounds, call it 5 kilograms, because big babies take longer to get out for reasons I trust I don't have to explain. There's a greater risk of the baby getting damaged. There's a greater risk of the baby having something like its umbilical cord get constricted if it can't get out easily. There's a greater risk of complications and ultimately a greater risk of the baby dying during birth. The minimum mortality, you can see, is right about here. It's about 7.5 pounds, which would be roughly 3.5 kilos. That's got the lowest mortality associated with it. That's a mortality of about 2%. And it just so happens that's very close to the actual mean birth weight. And the mean birth weight is shown by this diagram that looks like a stepped pyramid. Roughly 20% of the population is born at about a birth weight of 7 pounds. There's a fairly small number of babies that are born very light. There's a small number of babies that are born very heavy. 11 pounds is about the highest possible that we ever see. And most people are babies that are kind of in between. My kid was right about here, 7 pounds 14. I don't know what I was, but most people are born kind of in the middle. And birth weight is partly heritable. People who were small babies have a greater tendency of giving birth to small babies themselves. And people who were large babies have a greater chance of giving birth to large babies themselves. That's not all there is to it, but there is a heritable component. And that makes this stabilizing selection because the mean is favored. Right? You have the greatest chance of survival if your birth weight is very close to the mean. And if your birth weight is far from the mean, if you're either very small or very large, you have an increased risk of death during the birth process. Everybody see how that's stabilizing selection. You're selecting against the extremes and favoring the mean. Finally, some cool studies on disruptive selection got done on an African bird called the black-bellied seed cracker. And Bates Smith went out and measured a bunch of bird beaks. And if you look at the data down below, the lower mandible length, you'll notice that it's fairly close to a bell curve. There's some that are really small and some that are really large, and most are kind of in between. The shaded parts of those bars measure survival. And I believe this had to do with the species of seed that were available. They happen to be either small seeds or large seeds, but not medium. The birds that survived either had a pretty small beak or they had a pretty large beak. But the ones in the middle that were neither one thing or another, they all died that year. You can see a similar effect on the lower mandible width in the upper graph. Although here, that graph already is not a simple bell curve. It's got two peaks. But you see that birds that had either a narrow lower mandible or a wide one were likeliest to survive. Birds in the middle, no go. There were no survivors there. Okay, and that would be disruptive selection. All right. Am I making a certain degree of sense? Probabilistic. In the Galapagos, one of the things that's been observed is a phenomenon called character displacement. If you look at the lower two graphs first, the lowest one is the island of Los Hermanos, and there's a small population of the small-beaked groundfinch, Geospiza fuliginosa, which is the one here that's shaded yellow or shaded gold. On the island of Daphne, there's a population of Geospiza fortis, the medium-beaked groundfinch. And you can see that on Los Hermanos and Daphne, the two populations have very similar distributions. The population of Geospiza fuliginosa on Los Hermanos looks like it's got a mean of about 9 millimeters. Looks like about the same, 9 to 10 for fortis on the island of Daphne. You see what I'm getting at? If I took these two bottom graphs and kind of superimposed them, those bars would overlap quite a bit. Yes? Now, if you go to the larger islands of Floreana and San Cristobal, notice something. Where you get both species living on Floreana and San Cristobal, the fuliginosas have smaller beaks and the fortis have bigger beaks, right? Like mentally take the fortis population on Daphne, that's the third from below, and then move up to the ones on Floreana and San Cristobal, that's the second from the top. Like compare this with that, and you'll notice that the beak sizes have gotten bigger on Floreana and San Cristobal. And the same thing here, beak sizes for the small beak groundfinch have gone from here to here. They've gotten smaller. Does everybody see that? What has happened is that selection has evidently acted to reduce competition. If you are a small beaked groundfinch and you've got a large beak, you may be competing not just with your own species, but with Geospiza fortis. If you are a small beaked groundfinch and you have a very small beak, then you have a greater chance of using a food supply that Geospiza fortis can't compete with. When this happens in ecology, we call it niche partitioning. Anybody heard that term? The example I always give would be what happened if we opened a bunch of shoe stores in Wallonia. Well, many of them would probably die out pretty quickly because there's not a whole big demand for shoes in Wallonia. But maybe the ones that survived would be the ones that specialized, that did, I think they call this market segmentation in business. So you might end up, instead of 3 general shoe stores that are all competing for the same shoppers, maybe you end up with one that sold work boots and one that sold athletic footwear and one that sold fancy shoes for a hot night on the town. Although in Wallonia, the hot night on the town would have to be in either Conway or Circe, and neither one of those. Okay, a lukewarm night on the town. All right, you're familiar with this so far. What's happening here is we're not seeing only niche partitioning, but selection is shifting those trait values, the beak sizes. Selection shifting the beak sizes around so that competition is minimized. And then the same thing happens if you look at that top graph on Pinta and Marchena. You have 3 species of groundfinch. And you'll notice that Geospiza fortis no longer has that tail extending towards the right, because the fortis with the really big beaks are now going to be competing with Geospiza magnitorostris. So if you are Geospiza fortis with an unusually big beak, you're going to face competition with magnitorostris. If you have a beak that's more ordinary for your size, you're not going to be competing with magnitorostris. So what's happened here is that selection is basically on Pinta and Marchena, you have these 3 separate species, and they've all got pretty neatly divided up ranges of beak size. They don't overlap. There's minimal competition between them. So that's kind of a neat example of selection acting on continuous traits. And again, Peter and Rosemary Grant are the ones who've been gathering data like this, because they've spent part of every year for the past 50 gathering huge amounts of data on Galapagos finches. Okay, got to give you guys just a little bit of math. Although I'm not going to make you actually work equations using this, but I need to make sure that we've got a common language for understanding what we're getting into. You take a bunch of data on some quantitative trait, whatever it is. In fact, thanks for the reminder, I need to do this. Tomorrow, when you come in, bring me your height. I assume you know how tall you are. Bring me your height. I've been taking these in inches because that's kind of customary in the US, but if you know it in centimeters, you know, I can do the math. You know, 1 inch is 2.54 centimeters. And yeah, if you're okay with this, I won't attach your name to it, but I want to record what your height is. So once I've done that, I'll have a set of numbers that express everybody's height. I can calculate the average height of the people in this class. And then for each one of you, I could take your height, subtract your height from the average. So if you were exactly average, that would be 0. If you're tall or you're short, that would be a big number. All right, square that number, and then take the mean of all of those square differences, and I get something called the variance. Intuitively, you can think of variance as a measure of how wide that distribution is. Let's say the average height in this class is 5'9". If everybody in the class was between 5'8" and 5'10", we would have a very small variance, right? That would be a very narrow bell curve. We'd all be very close to the average. On the other hand, if our average was 5'9", and we had somebody in here who was 4'10" and somebody who was 7 feet tall, that would give us a much wider variance. Right? The average might not be any different, but the variance would be much greater. Am I making sense? You can think of the variance as being a measure of how stretched out or how squished in that bell curve is. The square root of the variance, by the way, is the standard deviation. And I know that's a stat that you've encountered before. Right? That's another stat that you can think of intuitively as measuring how stretched out that bell curve is. And for any data set, we can calculate the variance, and we can call that V sub P, the total phenotypic variance. P stands for phenotype. Now here's the thing, some of that variance comes from genetic variance in the population, and some of it comes from environmental variation. Okay, we are all different heights. Why are we all different heights? Some of the reason why we're all in different heights comes from the genes we inherited. Some of us had taller parents, some of us had shorter parents. Some of that variation depends on the environment, possibly childhood nutrition. I hope this didn't happen to any of you, but if any of you were starving as a child, if any of you spent, had chronic malnutrition and didn't get enough to eat, for example, you're going to grow to be shorter than you would if you had had a bountiful, nutritionally balanced diet as a child. When I sample the heights of UCA students, I tend to assume that people did not go through that kind of huge variation in their childhood nutrition, but maybe some did. So some of what makes us different in height comes from variance due to the environment. Some of what makes us differ in height comes from variance due to the genes we inherit. And we can think of that total variance as the genetic variance plus environmental variance. For some traits, the environmental variance might be extremely low. Like, for example, the number of your noses is governed virtually entirely by the genes that you've got, right? Everybody's got one nose, okay? And like raising you in a different environment is not going to make you sprout extra noses, as far as I know, right? Okay, so there's no environmental variance in the trait number of noses. That's entirely due to your genes. Other traits might be entirely environmental. Most are, traits that have a lot to do with the environment might be things like your build, whether your environment has you lifting heavy weights and running stadium steps every day, or has you lying on the sofa drinking Coke and eating potato chips every day. So weight has an environmental component. It also has a genetic component. And exactly where that balance is different for every trait. One that's actually been looked at. There was a study applying this to a lot of human traits done by a guy at the University of Minnesota named Thomas Bouchard. And they've actually identified some flaws in his study, and I might come back to that. But one conclusion that seems to work is they looked for variance in the religion that you follow, and they found that there's virtually no genetic influence on that at all. Whether you are a Baptist or a Buddhist or a Methodist or a Mormon or a Minervan Wiccan is entirely due to the environment that you're raised in, and there's no genetic contribution to that at all. So what church you go to is pretty much entirely environmental. How many noses you've got is entirely genetic. Many traits are somewhere in between. And you could say that genetic variance would be the variance in the population if all members had an absolutely identical environment. We can do this a lot in ecological studies. You might take a whole bunch of plants and raise them in a single bed or a single garden and make absolutely sure that all of them are getting exactly the same soil, the same amount of fertilizer, the same amount of light, the same amount of water. Like you could plant 10 tomato plants in one garden, treat them all as exactly the same as possible, and then any difference in the tomato plants must be due to the genes because there's no variation in the environment that you're giving them. So VG would be the variance if all members of the population had an exactly identical environment. VE, variance due to the environment, would be variance if all members of the population had identical genes. So here you could take, let's say, cuttings from the same plant which would be genetically clones of each other, and plant one in the desert and one in the rainforest and one on the lawn and one in the Arctic, and plant them in all sorts of different environments. And if you did that, you would get variants in the plants that grew, and it would entirely be due to the environment, because all of those plants are genetically identical, because they would all be cuttings from one plant. Am I making sense there? So genetic variance is the variance if all members of the population had an exactly identical environment. Environmental variance is the variance that you see if all members of the population had identical genes. The sum of the two is what gives you total phenotypic variance. And again, for some traits, VG is practically 0. For some traits, VE is practically 0. For most traits, there is contribution from both. Okay, let me see here. 1203, that's actually, I hate to let you guys go early because you're not getting the full impact of my teachings here. I've already let you go early a couple of times, so I should probably keep you another hour to make sure you're getting your money's worth. How about it? Should I keep going? Yeah, some questions I don't need. If I know the answer, I don't need to ask the question. So I'll stop recording. I'll stop recording.